In this video, we examine in more details than previously the pozzolanic nature of some supplementary cementitious materials, or SCMs. As explained in our previous video, SCMs are used as partial replacement for clinker to reduce the environmental footprint of cement, in particular CO2 emissions. Pozzolans were first exploited in ancient Greece and Imperial Rome, where volcanic ash and calcium hydroxide, provided as slaked lime, were found to harden in presence of water and in absence of air. In modern cements, pozzolans react with the calcium hydroxide provided by the hydration of cement. Our video on this historical development shows how this reaction leads to the formation of calcium silicate hydrate, noted CSH in cement chemistry. The dashes are included because of a variable stoichiometry that can additionally incorporate substantial amounts of aluminum, in which case this phase is then noted cash. The simple reaction between amorphous silica, calcium hydroxide, and water leads to an increase in solids volume of about 40%, which is much lower than the 114% obtained by tricalcium silicate, the main phase in ordinary Portland cement, whereby this tricalcium silicate, or C3S, reacts with water to produce both CSH and CH, that is, Portlandite. Using a representative composition of CSH given by C1.7 SH4, that reaction becomes C3S plus 5.3H gives CSH plus 1.3 CH. The key feature of pozzolanic SCMs is that the amorphous silica they contain, and that we note S, reacts with calcium hydroxide to produce CSH, whereby 1.7 CH plus S plus 2.3 H gives CSH. Importantly, as more and more clinker is replaced by SCMs, two things happen. First, less calcium hydroxide is produced, and second, more amorphous silica becomes available. Both changes imply that there is, in principle, a maximum level of clinker substitution by pozzolanic SCMs above which all calcium hydroxide gets consumed, so that excess SCMs cannot react fully. To highlight this, let us combine both previous reactions to obtain a full consumption of the calcium hydroxide. 1 mole of C3S produces 1.3 moles of CH. Additionally, 1.7 moles of CH can react further with 1 mole of silica to produce 1 mole of CSH. So we need 1.3 over 1.7, or 0.76 moles of S to consume the 1.3 moles of CH produced by the hydration of 1 mole of C3S, which gives an overall reaction for the hydration of C3S coupled with a complete pozzolanic consumption of CH as C3S plus 0.76 S plus 7.06 H gives 1.76 CSH. So 1 mole of C3S can at most react with 0.76 moles of silica. Let us convert this to mass units with respect to 1 gram of C3S. For this, we first multiply each term by its molar mass, respectively 228, 60, 18, and 227.2 grams per mole to obtain stoichiometric coefficients expressed on a mass basis. Dividing each of these by 228, the equation refers to the reaction of 1 unit mass of C3S, whereby 1 unit mass C3S and 0.2 mass units silica and 0.56 unit mass water give 1.76 unit mass of CSH. This highlights that 0.2 unit mass of silica react per unit mass of C3S. So any amorphous silica exceeding 20% of the C3S in a blended cement will a priori not react. In reality, these limits are generally lower, as in addition to stoichiometric considerations, the slower reaction kinetics of pozzolanic SCMs poses another limit to the amount of material that can react in a practically meaningful timescale. We also note that in real cement, C3S represents 65 to 70% of the mass. C2S not only has a much lower abundance, but is not favorable towards pozzolanic reactions, as the amount of CH produced is much lower, 0.3 moles per mole of C2S, as opposed to 1.3 moles per mole of C3S. Having said this, we note that the pozzolanic reaction more generally leads to a CSH composition incorporating fair amounts of aluminum and noted cash. So the above number should only be taken as indicative, even if it points to a much more important and fundamental issue, which is that in blended cements, the pozzolanic reaction is constrained by the amount of portlandite that cement hydration can produce and by inherent reaction kinetics of the pozzolan. Moreover, we note that many pozzolanic or partially pozzolanic SCMs can have a high content of alumina. This can be highlighted in the ternary diagram introduced in our previous video. It shows, for example, that typical alumina contents in metakaolin are about 45%, while in fly ash they can vary from about 25 to 40%. For most substitution levels, this would exceed the incorporation capacity of the formed CSH, so that there is an open question about the advent of this additional alumina. As will be discussed in our subsequent video, this also represents an opportunity to precipitate additional hydrates that can enhance the space-filling capacity of blended cements. In conclusion, the pozzolanic reaction concerns many supplementary cementitious materials to various extents. It takes place between the calcium hydroxide produced by cement hydration and the amorphous and/or poorly crystallized silica-containing phases of the SCMs. This puts an upper limit to the degree of clinker substitution above which SCMs will only partially react. However, many SCMs also include aluminates, which offer additional reaction routes, as discussed in our subsequent video.